this conference is doing is maintaining the notion that the two things are separate. And they're not. Until the spiritual religious community as a community comes on board across all traditions and says, this is what our scriptures are about, and this is what we say, you are not going to know why you can't get people to agree on these issues.
Hi there, I'm really happy to be here today to tell you about one of the impacts climate change is having in the ocean that really hasn't had as much focus as I wish it and I hope it will have in the future. So climate change has 3 impacts in the ocean. It causes the oceans to warm, it causes them to become more acidic, so decrease in pH, and it also causes them to lose oxygen. And so today I'll be focusing on the loss of oxygen from the oceans. And we know that scientifically as ocean deoxygenation. And so the ocean actually takes up more than 90% of the heat that's produced from anthropogenic CO2 emissions. And when the ocean warms, it has some really important consequences, like deoxygenation. And unfortunately, this is a fairly new problem. Even scientists have only started addressing it in the last 20 years. And so it hasn't received quite as much attention. But oxygen is fundamental for most life. We breathe oxygen, fish breathe oxygen through their gills. Pretty much all of the organisms you see in that coral reef require oxygen to live, and so oxygen is very fundamental. However, climate change actually causes oxygen levels in the ocean to decrease, and that's mostly due to warming. And we've actually seen that in the data. Globally, we have seen that the oceans are losing oxygen, and we've already seen biological consequences of this oxygen loss, because again, oxygen is very important to support life. And the groups that are most sensitive to loss of oxygen are actually fish and crustaceans. So crustaceans being our crabs and our lobsters. So these are the groups that are really important for our fisheries. And so that's why a lot of countries should actually be interested in what's going on with oxygen loss on their coastlines and in the open ocean. And so let's just take a moment and take a breath and think about what's in the air that we just inhaled. So about 21% of the air that you just inhaled is oxygen. And as Carol Turley will tell you, there are 2 lungs on this planet. One of the lungs is the terrestrial lung, and it's producing about half of the oxygen, and the other lung is our ocean lung. That's all of the algae that grow in the oceans, and that's producing 50% of the oxygen we breathe. So a lot of the oxygen that we're getting is actually coming from all of these small phytoplankton in the ocean. In the ocean, there is oxygen, but it's there in a dissolved form, and it's much harder to get out of the water for marine organisms that live in there. And oxygen content in the ocean is dependent on the temperature, the amount of mixing that's occurring at the surface, and then the biology. So biology produces oxygen through photosynthesis, and it uses up oxygen through respiration. So we respire, and all of the organisms in the ocean also respire, thereby using oxygen. And climate change has a negative impact on all 3 of these. And so we'll just do a little intuition building so we can all become comfortable with why climate change would negatively impact oxygen levels in the ocean. So first of all, warm water holds less oxygen. We can do many experiments in the lab. It's a very simple physical property, and we see that when temperature increases, the amount of gas that water can hold decreases. And so because of that, just simply when you warm the water, it's going to be able to hold less oxygen. And we can actually see this in the lab, but then we can actually see this in the data from the ocean, where the tropics in light purple are areas with low oxygen, and the tropics are the areas with the lowest oxygen at the surface, because warm water can simply hold less oxygen, whereas polar regions have higher oxygen content, just because of the property that cold water can hold more oxygen. And then warm water is harder to mix, so when you get warming at the surface from climate change, it becomes more difficult to mix that water. When you can mix more water, you can get more oxygen into the water from the atmosphere. When you can mix less water due to that warming, you get a stratified water column. That means that everything outside of that mixed layer is no longer in contact with the atmosphere. And a lot of biological respiration is going on at those mid-depth levels. So if you can't mix the oxygen in there, it's going to get depleted much more rapidly. Another reason why warming leads to more oxygen use is because when it's warmer, you actually breathe more, you respire more, you use more oxygen. And so that's what's going on in the ocean with all of the organisms that live there. The ocean is full of bacteria, so there are about 1 million bacteria in every milliliter of seawater, and all of those bacteria are utilizing oxygen. So that, and when the temperatures increase, you also get increased respiration. And so a lot of times you get increased respiration in areas where there's high productivity. So whenever you have a big algae bloom, for example, and once the algae bloom sinks out of the water column, it gets decomposed by all of those bacteria, and that leads to a reduction in oxygen. So whenever you get increased nutrients, whether that's through sewage runoff or fertilizer runoff, or whenever you get increased nutrients due to upwelling, so coastal circulation, nutrient-rich water coming up, you're going to be in a situation where you have high surface productivity and then more decomposition at depth. And so coastally we have a lot of hypoxic areas. So hypoxia is simply defined as an oxygen concentration that's detrimental to life. So in most areas, most organisms can't live in a hypoxic zone. Some are specifically adapted for it, but most animals can't live in those areas. And so in red you can see all of the coastal hypoxic zones. There are more than 400 identified now, and so these usually correspond to areas with dense populations. And so these are primarily driven by a lot of nutrient runoff from our farms, from sewage, and so most parts of the world with dense population have these coastal hypoxic zones. And so if you actually go on Google Earth and you go into Google Ocean, you can take a look to see all of the hypoxic areas that have been identified in your own area. So that's us at the National Stadium, and you can see the Baltic Sea actually has quite a few hypoxic zones. There are also open ocean low oxygen zones. We call these oxygen minimum zones. And they're naturally occurring there because we have really nutrient-rich water at the surface, and once we have high productivity at the surface and it sinks down and gets decomposed, it utilizes a lot of the oxygen. And so we have these large oxygen minimum zones, particularly in the Pacific. And so in this map, everything that's not gray is a part of the ocean that has hypoxic waters. And so we see really large areas of that in the Pacific, in the Indian Ocean, and then we also have hypoxic areas off of the west coast of Africa. And so where these hypoxic zones actually butt up against the continental margins, that really impacts our fisheries, because a lot of our fisheries target the continental margins. And these are large areas where most fish that we like to fish can't live. And so the total hypoxic area on the continental margins, so a lot of the places we like to fish, it's greater than the area of Poland and France combined. So you're really talking about large areas where most fish that we like to fish can't live. And so not only are they large in area, they're about 8% of the total ocean area, but they're also very deep. So you can have parts of the ocean where you can have 1,000 meters of water that's hypoxic, which can't support most normal aerobic life. And so one of the main points is that this is a very widespread problem, and probably whether you have a coastal hypoxic zone due to runoff or you have an oceanic zone due to your or an oceanic low oxygen zone due to your location, most coastlines actually have a low oxygen problem. And this low oxygen problem gets exacerbated when you experience surface warming because of the properties of how warming affects oxygen content in water. And so we've actually seen in our data that there has been a decrease in oxygen, and the new assessment IPCC Assessment 5 report actually predicted that by the end of the 21st century you'll see a 3 to 6% decline in global oxygen levels in the ocean. But this is just an average value, and so what you actually see in this graph, in the blue, on the top panel in the blue, you see areas that are already low in oxygen, and then in the second panel, in the blue, you see the areas that are going to lose the most oxygen and have lost oxygen already. And what you can see is that the areas that are already limited on oxygen are the ones that are losing the most oxygen. And so that's important. And you can actually see the expansion of these low oxygen areas through the water column. So between 1960 and today, you can see that the depth occupied by these low oxygen hypoxic areas in the water have expanded. And so what that means for us on the coastlines is as these areas expand, they also shoal, so they become shallower. They get closer to our coasts, and our coasts now actually face this low oxygen water that is coming up and affecting some of the fish. And we've seen off of the coast of California in the last 22 years a 21% decrease in mean oxygen content at about 300 meters, and coastally a shoaling of about 100 meters of the hypoxic layer. And so where the depth of the hypoxic layer is what really affects a lot of your coastal organisms. And so what we can see when we look at physiology in the lab is that there are certain groups that are most sensitive to low oxygen. And we can look at this in terms of lethal concentrations, and so what causes an organism to die, or we can look at this with sublethal concentrations, so what causes an organism to grow less or to reproduce less. And we can see that for both of these, crustaceans and fish are our most sensitive groups. And we can see that in the lab, but we can also see that in the field. We have mortality events, large mortality events in the Gulf of Mexico. When you get a hypoxic area, you have a low oxygen event, you have dead fish. This is a really fast impact. We also see that off of the coast of Africa, where there's low oxygen water that shoals. Crustaceans, lobsters will just walk out of the ocean because the oxygen is too low for them, and you'll have a widespread mortality event. And so we can see this most recently off of Oregon, where before the Oregon coastline did not have a lot of anoxic and hypoxic events, but recently, since 2002, because of the shoaling of this oxygen minimum zone and this low oxygen water, they've actually been experiencing a lot more low oxygen mortality events. And starting in 2002, they saw 75% mortality of the Dungeness crab, which is a really big, important fishery off of Oregon. And then also in these ROV surveys, you can see a healthy fish community prior to 2002, and then pretty much all of their ROV surveys after 2002 saw a lot of dead fish and invertebrates along the bottom because of these low oxygen events. And so what that means for the greater ocean, it results in habitat expansions and contractions. So there's some organisms that actually really like low oxygen because they've been adapted to it through evolutionary time. So this fish on the right actually does great with very low oxygen concentrations. And so organisms like that will see their range expand. But organisms that need high oxygen to survive, and so those are our tunas, our billfish, they actually are experiencing habitat contraction because all of a sudden they can't use as much of the water column as they did previously. And so we've already seen a 15% reduction in the habitat of tuna in the Atlantic because of the expansion of these low oxygen areas. There's also been a decline in mesopelagic fish. So these are small midwater fish that are really a very important component of the food web. They feed everything at the top levels of the food web, and so they're very sensitive to low oxygen. And then also we've seen habitat expansion of the Humboldt squid. So the Humboldt squid can do well in low oxygen conditions, and it actually has expanded all along the west coast of the US. And they compete with hake, and they also eat hake. So the hake fishery has not been doing as well, but the fishery on Humboldt squid has been doing better. And so a really important point is that low oxygen areas are carbon dioxide maximum areas. Whenever you use oxygen, you produce carbon dioxide. That's just through respiration. And so whenever we see an area that's low in oxygen, it's always high in carbon dioxide. So when we see the shoaling of these low oxygen areas, we actually see the shoaling of very low pH water. And so that's exactly what we've been seeing off of the west coast of the United States, where some of the water that's coming up is 7.6, 7.75, very, very low pH. And what that also means is it has very high CO2 concentrations. And so some of these waters are 1,200, and for example, surface is 400 parts per million. And so this is actually water that is net fluxing carbon dioxide out of the water instead of taking it up. So there are some important feedback implications. So we really need to pay attention to ocean deoxygenation because it has very important biological effects. We know that it's declining, and we know that it will decline in the future with surface warming. And we know that it probably will have some important impacts for a lot of coastal economies. However, because it's such a new topic, it really hasn't had too much of a focus, and it didn't make it into the summary for policymakers, even though it's really a problem policymakers should be thinking about because it can impact their local economies. And so small changes in temperature can have very drastic impacts on oxygen content. So just a 1 degree increase in surface warming will triple your suboxic zones and increase your hypoxic areas by 10%. We know that it has profound consequences on biodiversity, on fisheries income, and We know that it also has environmental feedbacks in terms of greenhouse gas emissions, because a really potent greenhouse gas, nitrous oxide, is produced in low oxygen areas. And in the historic record, we actually see that oxygen-depleted areas in the ocean are very tightly correlated with warming periods. So we know how this works in the past. And so with that, I would just like to say thank you for listening to this presentation. And I'm here as a part of a group of Scripps students. We're graduate students, and we really want to try and communicate our research to more of a public policy audience as well as a public audience. And so there's more information about how climate change is affecting the oceans at this website, oceanscientist.org. And also there's an oceans booth here, 102, on this floor. So if you have any other questions about ocean impacts of climate change, please come and talk to us. So thank you.
Architecture is both kind of like one of the biggest responsibilities to carry when you consider the human development and the effects of human development, when you consider urbanization, population growth, the need for further and further and further development. And when you acknowledge that sort of the resources that are being consumed, wasted through construction, demolition processes, all of this, and you consider energy and climate change and carbon, etc., through the operation of buildings, you know, the responsibility upon the architects has changed in profile. There is no longer that kind of art for art's sake. We actually have a greater responsibility, and whilst the need for art is there, and make no mistake, there's, you know, our cities need to reflect our aspirations, they need to reflect our society, they need to reflect what is good about human creativity and nature. There is another layer of thinking that has to be brought to architecture in this current world, in these days now, which is a very much a social and an environmental responsibility that cannot be shirked and has to be addressed. And I just want to convince as many young up-and-coming architects as possible to think about architecture as a very, very important role player in the world going forwards, in terms of that responsibility, both in an artistic sense and a scientific sense, in terms of performance and everything else. You know, there's an old modernist architecture axiom that talks about form follows function, and I prefer to think in terms of form follows flow. And I think about that in terms of the way the sun energy flows across a site, the way wind flows across a site, water, even people, even money, even all sorts of things. So one can sort of underpin a design in its social, economic, environmental context by considering the various different energies that are flowing and how to harness the power within that in order to generate architectural form and meaning. So you know, it's very much context based. So I teach, and what I try to impress upon my students is that there's kind of three role players in essence in the architect's visualization or understanding of a project, and that would be the physical context of the project, so the piece of the planet whereupon it's going to happen, whether that be urban, rural, or whatever. That piece of earth will have various different attributes and sort of qualities about it. Then there's the brief or the program or the client of the project, and their needs out of the project is a very big design driver that architects can actually use to generate form, obviously. And then there's the architect themselves and what they bring to that process in terms of their identity, their worldview, their philosophies, their creative impulses. So it's sort of a very nice process whereby I see the architect as kind of like a matchmaker between a piece of ground and a client with a need, but that matchmaking happens through a very personal engagement with the project by the architect, bringing their own sensitivities to that project. We have a world now, and we have this thing called climate change, and the reality is that 40% of climate change is actually caused by architects. 40% of the world's energy is used in the operation and maintenance and production of buildings. So I point the finger at architects and I say it's your fault. And then I understand that, particularly in South Africa, architecture is being taught the way it was today, the way it was when I was a student. And what I'm saying is that there needs to be a complete and utter paradigm shift in the way that we understand architecture. Once you realize, or you point the finger at architects and say it's your fault, then something has to give, something has to change. So what I'm really sort of quite passionate about is bringing sort of dismantling this ivory tower idea that architects have, that they are these wonderful creators who visualize these beautiful constructs and they get realized. And I think, the way the world is heading is that in actual fact buildings should be designed around a table with a whole bunch of different expertise, including biologists, sociologists, physicists, and as well as engineers and architects and everywhere else. But again, bringing in that sort of systemic understanding of design and problem solving. And it's not really about creating objects anymore. The time for that is gone. Yes, there are huge aesthetic and meaning and identity responsibilities on the architect to create beautiful buildings, but beauty is in the eye of the beholder, and that is a sort of subjective debate that can go on forever. So what you can do is you can justify a design through process, through an understanding of what it is that you're doing and how you arrived at that solution. And provided that there is a sort of a sensitivity and a sensibility about aesthetics and about composition embedded in that understanding, then you should be okay. And that's kind of like where I try and focus my work and try and focus my teaching, that I try and bring to students a new methodology of architecture whereby they can actually explore these contextual issues in a lot of depth, and out of those issues they can draw a systemic understanding of how the building needs to operate and what it needs to produce or do or provide, and those considerations are then the generation of form, and through that generation of form the architect brings a sense of identity and meaning and purpose to that resolution. So it's a quite a different kind of approach where there's a lot less ego involved and a lot more subtlety in sort of the generation of form and identity in architecture. Students are so keen to learn this stuff, and that's in South Africa there just is not the capacity amongst the teaching staff. They don't know. They know what they were taught, and they've practiced the way they've taught, which is about meaning and identity and art and creativity. And what I'm saying is, that's all critically important, but there's absolutely another layer that everybody's running around designing vehicles with square wheels. That's what it basically amounts to. They're beautiful, beautiful cars, but they've got square wheels, and they don't actually work. We've got office buildings in Joburg that in winter, they get heated up in the morning, and they get cooled down in the afternoon, because they're so designed not around performance, around the idea of creating comfortable spaces inside with an outside environment that you have to understand and take into cognizance. So I see that outside environment as a resource, as a system of energies to use, to harness, to create comfort inside. Whereas most architects see it as kind of like an enemy that has to be shut off, and then we switch heaters on and we switch air conditioners on and we make this false environment on the inside. And that's not necessary. There is this filter, this relationship that could be developed between the inside and the outside of buildings, between the internal climate and the external climate, in terms of creating comfortable spaces that meet human needs for comfort and shelter. That's the biggest problem. That is the biggest problem, is that we actually need we need to intervene on those buildings in very, very clever ways, and that's not always very easy. But it can be done, and that's actually where I want my research to start going, is to start saying, okay, it's easy to design this perfect city on this green field site and reimagine how Joburg could have been developed, but this is how it is now. So how do you apply the same thinking at a building scale, at a room scale, at a street scale, at a neighborhood scale, at a district scale, at a city scale? How do you kind of reimagine the current infrastructure being messed with, eroded, sort of attacked, modified to be more responsive to the overall systemic understanding of what's going on? So that's kind of like where I'd like to take my work. The way I often talk about my buildings is that they sit in a landscape and they relate to that landscape very much, or they evolve in that landscape during the design process, very much the way an organism evolves in its ecosystem. So they tap into the available resources, and they concentrate on cyclic relationships, and these things are exploded up from an ecosystemic, traditional ecosystemic understanding to a more sort of to a more human contextualized ecosystemic understanding. So things like money, aspiration, purpose, meaning form part of that contextual relationship that the building positions itself within and responds to. There was one project where the client came to me and his objective was to have a house that was independent of the city council and was autonomous, what we call an island home. And because he didn't have trust or faith in the city council in the years to come. And that was a statement at the beginning of the project. By the end of the project took 2 years to design, and by the end of the design process he was a completely converted environmentalist, and he had taken on all of these other softer tissue agendas about responsibility, custodianship, and etc. So that was really a fantastic kind of process. Also, he was a very wealthy man, and he spared no expense at achieving his objectives, which is an incredibly high performance house. It was a private house, and one which was autonomous, so it makes its own electricity, it makes its own water, it treats its own waste, etc., and it's in a suburban context here in Johannesburg. And so that was like quite an interesting project, and what was really fascinating about that was the kind of aesthetic ideals or the aesthetic identity that came out of that design process was very much a performance-based concept, again realized. It could have been realized in any number of ways. So the way it gets realized is influenced or shaped or sort of pushed by both my sensibilities and the clients. So it was quite nice in that sense, and it's for me it's a nice project, and I was really, really fortunate that to be given that opportunity to actually work something through right to the very nth degree of realization. So it was a very satisfying process, and kind of like it was from there that my interest then moved on to cities, because I kind of like felt like, okay, that's cool, nailed it, time to get on. You know what I mean? My interests have quite largely, or are busy largely, moving from understanding buildings in this way to now starting to look at cities in this way. And in fact, I'm kind of like starting to research and focus on the idea of how we as people can develop sustainable cities which respond to this contextual understanding of ecosystemic, in terms of natural environment, human-made environments, things like politics and economics. I'm very interested in biomimicry, and there's the biomimicry. There has been a city designed upon biomimicry principles, It's also been used in Cape Town for the upgrading of certain areas. So those kind of projects one finds really, really interesting. I don't, I kind of like take a slightly different slant to that, because as an architect, my interest lies in a range of influences and aspects that drive a design process, whereas biomimicry is really, really very specifically focused upon a specific kind of methodology, whereas I've kind of developed my own methodology, which would include things like biomimicry, sustainability as understood in various different ways. So I mean, there are lots of architects that I look up to, although I'm notoriously bad at remembering names of projects and people. I mean, Norman Foster is somebody who I think I really sort of kind of like admire the way he approaches projects. Ken Yang, Renzo Piano. So these guys kind of have they have a very natural way of developing a design, which in a way, one kind of conceptual understanding or solution for a project enables a whole range of different factors or considerations that they are encompassing. And I think that that's a really kind of nice way to think about architecture. What I really kind of like push against, what I really don't like, is this very sort of form-based, the creative impulse that many architects have to build monuments, basically what I call monuments to their own egos and their own creativity, and these sort of sculpturesque objects. And I don't see architecture as objects in space. I see them as an organism that ties into an ecosystem in a whole range of different ways. And it's very kind of like monodimensional to think of it as an object. And very seldom do I have an idea of what the shape or form of this building should be. It usually evolves out of a process. And I'm very interested in that, in how the aesthetics and the design look and feel can actually evolve out of a sort of a methodology which is very much kind of like science underpinning, the science of the performance of buildings and the ecology of buildings, underpinning a kind of a conceptual, artistic, personal impulse to generate. You always have some kind of a personal idea of, the same solution could be solved that way or this way, but you prefer this way, because I prefer to think of that in terms of what other options does it open up, what other design opportunities does this option or that option open up. But nevertheless, there's always some kind of materiality or sort of ideology or philosophy or aesthetic that underpins the sort of objectives that you're aiming towards in the design of a building. My whole theory about cities that I'm busy working on basically kind of like looks at ecosystems, natural ecosystems, and how organisms evolve within those ecosystems. And whenever conditions change, you'll see certain species die out, or certain species will proliferate and prosper and flourish up to a certain point, but then when they reach over a critical point and they start actually damaging the ecosystemic whole, they start to die back. So nature has these wonderful sort of self-governing mechanisms. So, and it's basically all built around water. I mean, essentially that's the bottom line of human existence. So, in a physical sense. So my kind of whole idea is really looking at cities in that same way. So, for example, municipal boundaries would be demarcated by watersheds, and each municipality would be responsible for